As I said, when a material is magnetized, you just expect that the magnetism or the magnetic strength of the material or the ferromagnet will increase. So we believe that it has increased. Now, when you get to this point, I told that you'll get to a certain point whereby uh, the the magnet or the material will be saturated. So this point, you can say that the saturating point. It is a saturation point. Saturation point. So this point we call the saturation point. And this point will be the saturation point, but in the opposite direction, because you know here is negative. So this saturation. This one too is saturation, but in the opposite direction. That means it has lost all its magnetic property to the extent that it has also become saturated in the opposite direction. And before I left, yeah, Ruben, talk to me. Ruben, your hands is up. Talk to me.
Sir, please, I thought that where the where the line met with the zero,
Is it here?
yeah, the return, no, yeah, the return, yeah, that place. I thought that was the place where it lost its magnetism.
I'll get there. Don't worry, I'll get there. I'll get there. And so that's how it works. You have a ferromagnet, and the ferromagnet, we believe that it's already it has a strong sense of getting magnetized. Let me put it that way. Now, when we add or when we apply a magnetic field, this is the magnetic field or the magnetic strength, and here is the density, magnetic density. And so you bear with me that when it is placed in an external magnetic field, definitely its magnetism or it will become magnetized. Let me put it that way, it will become magnetized. And so when it become magnetized, the more it's remain in the or it keeps being in the magnetic field, the more its magnetism gets increased or keeps increasing. Now we get to a certain point whereby it becomes saturated. That means no matter the amount of this thing, magnet field you add or you apply, it won't have any effect on it. It becomes impervious to the magnetic field. Let me put it that way, because it is satisfied. Now, when the magnetic field is now removed, we will bear with me that immediately the magnetic field is removed, at least there will be a reduction of the magnetic strength now of the material which has been magnetized. But because it is a ferromagnet, it won't lose all its magnetism at once. It will start from a process, so it will still have some of its parts or some of its atomic dipoles being aligned, and that will still contribute to its what do you call it? Its magnetic field, remain magnetic field. Now, when it gets to this point, that's what we call the retentivity. That means the retained magnetic field in the ferromagnet, even after the external force has been removed. So when you get this point, that's what we call the retentivity. That's the point where some of the materials are retained. Now, when it crosses this retentivity, then that means it's going to the negatives. That means its magnetism still keeps decreasing or still keeps falling. Now, when it gets to this point, or when it gets to this point, then we believe that now its magnetic is still a zero. Its magnetic or the magnetic resultant here is zero, or the percentage of magnetism in it is now zero. Now, if it still further decreases, or if it still further keeps deteriorating, then that means it starts moving in the negatives. Now, when it starts moving in the negatives, then we start moving from zero to the negatives. And so then we get to now it will get to a point where it will become saturated opposite. What do you call it? Becomes saturated in the opposite direction. And when that happens, now when you get to this point, it is more or less like this. Nothing will you do that will have any effect on it. Now let me give you an example. The other day I was teaching ways of magnetizing and demagnetizing a material. And I told that when you're magnetizing a material, we have various methods that we use in magnetizing material. The first one I said is by the electrical method. And so, for instance, when I put my the nail, which is a ferromagnet, or the iron, which is a ferromagnet, in an electrical method to be magnetized or to get magnetized, you bear with me that its magnetism will increase. Now, when I decide to reduce or just remove the wires and everything, or spoil the connection, that means I've taken away the magnetic flow from it. You just believe that some of the magnetism was still retained. And when it gets to when it takes a longer time, it will get to a certain point where it will fall to zero. Then that means there's no magnetism in it. Now, when we still say that, okay, let's keep hitting the material to still further deteriorate every dipole or everything in it, then that means already now the magnet is not in it, but you still keep hitting it, or you still keep hitting it, or you still keep mishandling it or anything, it will now start moving in the negatives. Then that means you're even destroying the little connections or the little alignments in the material, which could have also contributed to a little magnetism in it. And so you get to a certain point whereby you would have destroyed everything in it, that anything you do won't even further affect it again. It will now become saturated in the opposite direction. I don't know if you get my point. So when it gets to this one, this is what we call the retentivity. This is what we call the retentivity. Now, this point, we call this point coercivity. Coercivity. And I'll explain what coercivity is. It comes from the word coercive. Coercivity. So you realize that as the magnetizing force is reversed, so here we are reversing the magnetizing force. Here we were increasing it. Here we are reversing it. Now, as the magnetizing force is being reversed, you bear with me that there's a curve. So the curve will move down, and it will get to a point C. So let's say there's a point C. You realize that in the first diagram I labeled everything. There will be a point C, and where the flux has been reduced to zero, you realize that here the magnetic flux has been reduced to zero. When it gets to this point, you bear with me that here is zero. So it has been reduced to zero. This is called the point of coercivity on the curve. Now, that's the reverse magnetizing force has flipped enough of the domains so that the next flux within the material is zero. That means it has even moved from all this point to this point, and now the next flux or the next magnetic strength of the material is now zero. Now, the force required to remove the residual magnetism from the material is called the coercive force. So you realize when you got to this point, there was something we call retentivity. That's what we call the retentivity. And the retentivity simply means that there's a certain residual, that means there's certain remains of magnetism in it. Now, the force that is required to remove it from this point to this point, that means remove the already or the remained or the retained, what do you call it, the retained magnetic strength or field in the ferromagnet to basically zero is what we call the coercive force. So the force required to remove the residual magnetism from the material is called the coercive force or coercivity of the material. So when it gets to this point, we are seeing that there's been a force that has been able to remove the little energy it's stored, or the little magnetic energy that is stored, to zero. And that force which does that is what we call the coercive force. Is what we call the coercive force. Now, as the magnetizing force is increased in the negative direction, that means as we keep increasing, now we realize that we are moving the negative. So as we keep increasing the magnetic force in the negative direction, the material will become magnetically saturated, but in the opposite direction, just as I've already explained. And that will reduce the magnetic strength. Reducing H to zero brings the curve at point E. And so that will reduce the strength to this point. And when we want to reverse the equation, then we will still have to now, when I say when it gets to the saturated point and I want to reverse the distance, then it will start the curve again. There's a loop. We call it the BH loop. That means the B stands for magnetic flux density, and the other one is magnetic strength, BH loop. So it's a loop. And when we talk of a loop, you know, loops are repetitive. They repeat itself. So when it gets to this point and you want to start the loop again, then that means we would have to add some magnetic force or magnetic field again to this thing. Then that means we would have to move from here, get to this point before you start the whole process, then get to the saturating point. Then when we want to reduce it, it will come here. So that is it. So this is what we call the hysteresis curve, or the hysteresis this thing. Everything about hysteresis you have to know, or you want to know. So when you're asked to write a little bit about hysteresis, you should be able to understand it based on how I explain it. That is when you have a magnet, a ferromagnet. It normally happens to ferromagnets because they are strong magnets. And so when you have a ferromagnet and you applied an external magnetic field, there will be an increment in its magnetic strength, and it will get to a point whereby it will get saturated, and the magnetic field won't have any effect on it again. Now, when the magnetic field is taken away, then definitely there will be a decrement in its magnetic strength, and we'll get to a point where we call the retentivity. That is a point where some little of magnetism has been retained. Now, therefore, that is required to remove that retained magnetic field to get it to get its net magnetic flux to zero is what we call the coercive force, or the coercivity of the material. Then you get to the now when you still keep increasing the magnetic magnetization of the force in the
So
negative
please, the
direction.
spelling of the coercivity.
C-O-E-R 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 coercivity. Oh, sorry. Coercivity. So C-O-E-R-C-I-V-I-T-Y. That's how it's supposed to be. Sorry. So I'm pronouncing it, but I'm spelling wrong. Coercivity. Thank you. So that is basically about hysteresis. And so I've explained hysteresis. I've explained everything you need to know about hysteresis, about the saturation point, the retentivity, the coercivity of the material, and the saturation at the opposite point. The residual magnetism is the retained magnetism here. Residual magnetism is the retained magnetism. I've already told you. Then we have one thing we have to also consider, the permeability. Now when we say permeability, it's a property of a material that describes the ease with which a magnetic flux is established in a component. And so the ease with which a magnetic flux is established in a component is what we call the magnetic permeability. When we say permeability, we know that word, the first time I heard it when we were defining, I think, is it osmosis? Osmosis. So when we talk of permeability, that means the ability of a substance or the property of a material, what do you call it? That describes the ease at which the magnetic flux is established in a component. That means that has to do with the permeability. So when we say the permeability is high, then we are just trying to say that it is easily magnetized. Let me put it that way, or it is easily influenced by a magnetic field. Let me put it that way. And so that is electromagnetic permeability. Now the vice versa will be the reluctance. And so when we say the reluctance, then it basically means that it's the opposition that a ferromagnetic material shows to the establishment of a magnetic field. So the opposition that a ferromagnetic material shows to the establishment of a magnetic field is what we call the reluctance. And it is analogous. When I say it is analogous, it is similar, or in other words, it is akin to that we call the resistance in an electrical circuit. So it is similar. That means you can relate it to the resistance. That's what we call the reluctance. So the ability of or the opposition offered to by a magnetic material to the establishment of a magnetic field is what we call the reluctance in the material. Now from there, let's also talk about uses of magnets. This one we are all going to talk about uses of magnets, because one way or the other, we know what magnets are used for. So I'll start. When I mention your name, you give me one. Ruben, one. You are the number one here. So Ruben, one.
So please, it is used in the in the pots to pick pots,
Okay, okay,
chemical pot.
okay.
Yeah, to lift the containers.
So the magnet is used to lift it, or it is used in a in a device to lift it, or the magnet is used to lift it.
Yes, it's used in a device to lift the containers.
And then what was that device? Those device, is it a crane
The
or?
crane. Yeah,
Okay.
the crane.
Hey, I've helped you answer my question. God bless you. You've tried. Bridget.
Sir,
Yeah. Some use of
sir,
magnet.
please, it's used in manufacturing microphones.
It's used in the manufacture of microphones. Yeah, correct.
Sir,
Daniela.
microphones or speakers. Aye.
Okay, God bless you. Daniela.
Sir,
Yeah, use of magnets.
sir, magnets are used to pick up pieces of iron from mixed scrap metals.
Okay, God bless you. Mildred.
Sir, please, magnets are used in microphones, speakers, and to produce sound.
Okay, God bless you. Irama, Ruben, God bless you too. Irama.
So they are used to separate magnetic substance from non-magnetic substance.
Okay, God bless you.
God bless you.
Harriet. Harry, baby. Maureen.
Sir, Maureen is not here.
Oh, maybe a network. So, just as we said, they are using magnetic recording media. And they are using the recording for the tapes, recording tapes, and so on and so forth. They are also using credit, debit, and ATM cards. And so they are using credit, debit, and ATM cards. They are using common TV sets and computer monitors. They are using that. They are using our speakers and microphones, just as you rightly said. They are using electric motors and generators. They are using transformers. They are using chucks. They are using compasses. That's magnetic compasses. They are using science projects. They are using some toys. They are using jewelries, some of the jewelries, and so on and so forth. And some are even used at the hospitals to detect what do you call it, materials or magnetic what do you call it, metals or magnetic material that may have entered your system. They use all those things, and it has a wide usage. So that is it. Now, from there, we also talk about.
Sir,
Yes, please.
sir, please, another one.
Okay, tell me.
Sir, they are used saving coins.
Okay, they are using saving coins. Now you have been using it, pa. God bless you. God bless you, pa. Well, after the class, WhatsApp me and PM me. Come enter my DM.
Okay.
Let me do you like small. So that is it. Now let's talk about electromagnets. Oh, electromagnets. Now, when we talk of electromagnets, we are just talking about electricity and magnets. Let me put it that way. So, magnets, electricity and magnet. Let me put it that way. So, if a coil is wound around a soft iron core, when you wound a coil, when we say wound, what do you call it? When you have a soft iron core, can be a nail, and you wound. When we say wound, what do we be a friend wound? When you wound around a soft iron core, and current is made to flow around the core, a strong magnet is produced. And so you realize that when we're talking about the magnetization, we said that when you want to magnetize a magnetic material, you pass it through the electrical method. Now, when the magnet this thing, that process what we call the electromagnetism. And so it is magnetized electrically. Are you getting it? And so the iron core acts as a magnet only when the current flows through the coil. And so it acts as a magnet when the current flows through the coil. The core quickly loses almost all its magnetism when the current is switched off. So it almost loses all its magnetism when the current is switched off. The coil is wound around the arms of the soft iron in opposite direction and has to produce the north pole. And I've already taught you this when we were doing magnetism. Now that's basically what we call the electromagnets or electromagnetism, having to do with the electricity and magnets coming to or having something in common. The relationship between electricity and magnets. So the electro comes from the electricity and the magnets come from the magnets. Now, use of electromagnets are they are used in electric bells, they are used in electronic earphones, and the industry for handling heavy objects made of iron or steel. We already said this. So these are one or two uses of electromagnets. Now, that's just a quick distance. Now let's do something called magnetic fields or electrodynamics. Magnetic field or electrodynamics. Magnetic field or electrodynamics. Now let's talk about magnetic field. Or we should save this for another time. So there's a full class on its own. Someone should. How many minutes have we used? Can someone tell me? Coming, coming home, coming home.
Sir, please, 26 minutes.
Okay, 26 minutes. So we have some more this thing. We have some more time, about 15 minutes. So let's try and see if you can do it. So let's talk about magnetic fields. Now, you already know what magnetic fields are. We said that magnetic field is a region around a magnet or a current carrying conductor in which a magnetic force is experienced. So the region around a magnet or a current carrying conductor where magnetic force is experienced is what we call the magnetic field. I've already explained this before. And so the region where magnetic influence or field is experienced most is what we call magnetic field. And we are going to talk about its operations, magnetic field. Now, from there, we said that these magnetic fields, because we don't see them, they are normally represented by magnetic field lines, or they are normally represented by lines. And these lines we call the magnetic field, magnetic lines of force, or magnetic field lines, or magnetic flux. And so the magnetic lines of force, these are lines drawn to represent a magnetic field in its magnitude and direction. And so they are normally drawn to represent the direction of the magnetic field and the size of the magnetic field. And so the magnetic lines of force, these are lines drawn to represent the magnetic field in its magnitude and direction. That means the lines, number one, talks about the size of the magnetic field, and it also talk about the direction of the magnetic field. And so that is it. So we spoke about magnetic fields. We've also spoke about magnetic lines of force. Magnetic lines of force. Then now we also talk about direction of a magnetic field. Right from once I told that this is the direction in which the small north pole tends to move when placed at a point. And so the direction in which the small north pole tends to move when placed at a point. So the other day I told you that normally when you have a magnetic field, it normally moves from the field normally moves the direction, it moves from the north pole to the south pole. I told you that. So when you are drawing or when you are representing the magnetic field, the arrows should always move from the north to the south. I've already told you that. Now we are also going to consider some types of magnetic we're also going to consider some types of magnetic fields. Types of magnetic field. There are two types of magnetic field. Magnetic field. Now the first one is the uniform magnetic field. We have uniform magnetic field. Uniform magnetic field. And you have the non-uniform. You have the uniform magnetic field and you have the non-uniform magnetic field. Now, then we are going to talk about characteristics of each. What makes it uniform and what makes it non-uniform. Now, definitely, you know, when we talk of uniform, then we know that it is ordered. When we talk of non-uniform, then we are talking about something which is not ordered. Now, let's look out for characteristics of a uniform magnetic field. And so, let me first take this one. Let me change the color too. Oh, no. Okay. So, what we have a uniform magnetic. Normally, the magnetic lines of force are parallel to each other. So the lines of force drawn are always parallel. When we say parallel, they have the same distance and they are parallel. So they never meet. Let me put it that way. And so the magnetic lines of force. So magnetic lines of force are parallel. Magnetic lines of force are parallel. Now, the lines of force are equally spaced. I've already said this. So they are equally spaced. The lines of force are equally spaced. And I also said that the magnetic field intensity, also known as the flux density or the magnetic induction, is constant everywhere, so that a moving charge particles in this field experiences the same force everywhere. And so the magnetic field intensity, or in other words, the magnetic density, is the same everywhere. So anywhere there's a charge or there's a particle, it experiences equal amount of magnetic field. And so magnetic density or field experience is the same everywhere. Magnetic field experience. The same everywhere. That's why it is uniform. Now, the magnetic lines of force have the same direction. I've already spoke about that. And they don't cross each other. They have the same direction. They don't cross each other. Now, examples of uniform magnetic fields are the field between the north and the south poles of a large permanent magnet. So normally the field between the north and the south poles of a large permanent magnet are normally considered as uniform. Are normally considered as uniform. So, for instance, if I have another one here. And if here is north and here is south, the lines of force that move from one point to another, from the north. So one moves here. Equally spaced, and let's let me. So let's see, here is north. Here is north and here is south. The lines of what that exists between this is what we term as uniform. Example is the magnetic field inside the solenoid. A magnetic field inside the solenoid. That one is also uniform. and the magnetic field between the poles of the U-shaped magnets. You know, magnets can be U-shaped, and so the magnetic force between U-shaped magnets is also normally under the uniform magnetic fields. Now let's talk about characteristics of non-uniform magnetic fields. Magnetic fields of force are not parallel to each other, and so this is basically the vice versa of the uniform. They are normally they are not parallel to each other. They can be represented by curved lines which are not equally spaced. So they can be represented by a curved line and which are not equally spaced. A moving changed particle in the field experiences available force at different points in this field. And so a moving change particle in the field experiences available force at different points in this field. So that means they do not experience equal magnetic field at every point. And so that is it. And the magnetic flux density of the this thing, it varies from point to point, as I've already said. Examples of this is magnetic field around a bar magnet, a magnetic field outside a solenoid. And so for instance, if I have a bar magnet, if this is my bar magnet, then you bear with me that here is my north and here is my south. Now, the force that moves from here, lines of force, magnetic lines of force, that moves from the north to the south around the bar magnet. You realize that these are moving, this is curved. Okay, and they are not equally spaced. This one is what we call the non-uniform magnetic lines of force, but they do not cross each other. They don't cross each other, but they are non-uniform. So you just bear with me that a particle that is around this area, because it is around the poles, will definitely enjoy higher magnetic field than that which is around this area. And so the magnetic field intensity varies. So that is it. But unlike this one, we said that the one in a U shape. So for instance, if you have a U shape like this, a U shape, the magnet definitely here will be the north and here will be the south. So this one, they are parallel. They are parallel. The spacing is also correct. This one is uniform. This one is uniform. This one's normally the one outside the magnetic, this even a solenoid, the one outside, not the one inside. The one outside they're all non-uniform magnetic. They all experience non-uniform magnetic field. And so that is it. And I think, let me see if I have some 2 minutes. And so next week or our next meeting, we are going to talk about magnetic flux and flux density. And we are going to do calculations. We are going to consider the Fleming's left-hand rule and I think the Fleming's right-hand rule or something. Then we are going to talk about, so we are going to do basically this thing, calculations. We are going to talk about torque on regular rectangular coil in uniform field. We are going to do some calculations there. Then we are done. Then from there we move straight to electromagnetic induction. Then when we are done with that, that's where we are going to talk about the Lenz's law, the Faraday's law, the eddy's current, and so on and so forth. Then I think we are done. Then we move straight to alternating current. Then we are done. Please, let's take note that we are at the end of the month. This week we are almost ending the month. Those owing me, pay me. Those who are not owing me, start preparing your parents' mind for next week. I spoke to them and some are not aware because you guys don't remind them, and I don't like disturbing parents and students that, oh, pay me and all those. I don't like it. But you know, we are all doing our best. I'm always in class. I'm always doing my best to at least this thing. So you guys should also, you shouldn't let me talk now. I should be calling your parents and all. I don't like those things. You know what to do. And this thing. And please, you also go to YouTube, you subscribe, and you get this thing. Right after this, I'll upload everything on YouTube, and you also do it. God bless you so much. I love you all.
So
Bye-bye.
the
Bye.
two parts, part 1 and part 2.
Is that yeah, kids? I'll upload all part 1 and part 2. I'll upload all.
Okay, sir.
Thank you.